Thanks a lot, Ariel, for the nice introduction, and thanks to the organizers for inviting me to give this talk. So, as Ariel mentioned, that I am working with the Feedback Consortium on the SOFIA C+ legacy project called Feedback, and today I will talk about the kinematics in massive star-forming regions. I will start with absolute basics by asking the question, what is kinematics? So it is the study of motion of gas in the interstellar medium. Now, if you look at this image here, this is an HST image of the Lagoon Nebula. And we have the bright stellar system, Herschel 36 here, which is pushing the gas around it in such a way that it forms this hourglass shaped structure called the Hourglass Nebula. And it is also pushing the foreground gas, which is seen in this darker color, away from it towards the observer. So massive stars are responsible for pushing the gas to form different structures or to break dense clouds. The next question is, why do we want to study kinematics? So this movement of gas due to massive stars, whether it is blue shifted, red shifted, it tells us about the direction in which this gas is moving and which also defines the geometry. For example, here we have the pillars of creation of M16, where the gas has arranged itself into these pillar-like structures, or the Orion Nebula bubble here, which has shaped itself into a shell. Then another important thing that kinematics help us to do is to do the quantitative analysis. We can do a lot of calculations like kinetic energy. We can find the expansion time scales of these bubbles or shells in the interstellar medium. It also helps us to determine physical conditions like finding turbulent pressures, etc. So today I will talk about the special case of RCW49, which is one of the most luminous massive star forming regions in our galaxy. It has a compact stellar cluster over here, which has 37 OB type stars and 30 early type OB star candidates. So it's a very powerful region. And because this cluster is giving out a lot of energy and injecting this energy into the system and the surrounding medium. It also has two Wolf-Rayet stars, one which is part of the cluster and the other is in the south. And it also has an O5 star, which is in the east. These different stars are shown here in these different colored asterisks. This is an RGB image. In red, we have the C+ emission, which is observed with the SOFIA telescope, and it is tracing the warm PDR shell, as also marked with the red arrow. This shell has a well-defined eastern arc, but in the west, we don't see this. Then in green, we have the 8 micron emission, which is tracing warm dust. In blue, we have the 870 micron emission, which is tracing these cold, dense clumps. So these different wavelengths, the emission in these different wavelengths is basically tracing different components of gas in RCW49. Now, Juan already gave a very good description of the great data in the previous presentation. So as he mentioned that great data comes in observation files and LMV cubes. These observation files contain individual spectra, and one of the spectra examples is shown here. This is a spectrum of C+ at 1.9 terahertz, and it is towards RCW49. I can quickly show you how you can do it if you have GILDAS installed on your system. You just have to open class and then you open the file by typing this command file in. And these files are basically with this extension of .great. You find these many observations are found. We can do list table of contents, which tells you the number of sources, the number of lines, backend setups. For now, I just want to do an average of everything that I have, and I want to plot it. And this is the spectrum that we get. So here on the lower x-axis, we have the rest frequency. This is the C+ emission line. On the upper x-axis, we have the velocity, and on the y-axis, we have the main beam temperatures. We can interchange the frequency axis to velocity axis by typing set unit V. V is for velocity. And if we do PL, which is for plot, again, we see that the velocity and the frequency axis have interchanged. So this was like a first look into the spectrum. I will also be sharing these small scripts that can help you to get started with your data. Like it has been mentioned that you can get, if you have your own data, you can use these scripts, or if you want to get the data from the archive, then again, you can use these scripts to get started. The second thing that we get with the great data are the LMV cubes. So these cubes have three informations. They have spatial information, intensity information, and velocity information. I will again quickly show you how you can use this, what commands you can use basically to view these LMV cubes. So one has to start the class session, and I'm just selecting the LMV file here. I have to do let name, and I type the name. Oops. Yes, then I have to give the type of the file, which is the LMV file. And then I just do go view, which brings me to this interactive session. And you can see that if I click here, then I get the spectra shown here. And if I go in the regions where there is no emission, then I only get noise. And in principle, there is no spectrum that you see. Okay, something we saw here. But if I go somewhere here, then I directly see two very bright velocity profiles. So one can have a look at the LMV cubes like this. Coming back to the presentation. Yeah, so again, we have this, I've written these small scripts everywhere where you can use them to see your own data. Now, these LMV cubes, as Juan also mentioned, can already be converted to FITS files very easily. And then you can use whatever tools you like. You can use Gildas like I did for this paper, or you can use Python that I'm also using right now. So in case you're using Python and you have questions, you can definitely approach me. You can also use DS9 to take a first look at your data, or any other software that you're comfortable with. Now let's start with the exploration of the kinematics in RCW49. The first step is to identify the velocity spread. For that, what you should do is you should check the spectra of the region. So here I'm plotting the spectra of C+, 12CO, 13CO of RCW49. This is the average spectra. And we can see that the velocity spread is from -30 to 35 kilometer per second. But within this range, there are multiple velocity components. It's like Gaussian profiles which are almost intermixed to each other. So it's a very complex set of gas components in RCW49. Now that we have the velocity spread, the next step is to make moment zero maps. What does that mean? That if this is the map you have, and for every pixel, we have an associated spectrum. For example, these different colored pixels have these associated spectra with it. And what we want to do is we want to get the area under the curve, which is integral of TdV, and for every pixel. And then we want to put it together to make our moment zero map. How can we do it? We can do it using Gildas again. I will show you a very basic way to do it. So we open a class session. The main command here is run moments, which will give you this dialog box. Now I've already filled these things in because I knew what I was doing, because I did it earlier. And for example, I have to, for the input file name, I select the LMV cube. For the output file, I select the same file. However, the important thing is that there should be no extension because run moments already put an extension to your file with its outputs. Then you specify the velocity range here, a detection threshold, and if you want it smoothened or not, it's up to you. I do OK, and the task was completed successfully. Now, these three files, the .mean, .velo, and .width files are the output files. The moment zero map is the .mean file, which I can see with let name. Let type would be mean. And I do go view. And here is our moment zero map. Coming back to the presentation. So here are the moment zero maps that I made. These are for C++, 12CO and 13CO. Of course, you can see that the color scheme is different. These maps look a bit more nicer than what I showed, but that's just beautifying your presentation of the data, and that you can learn through the tutorials, which are already mentioned in the resources webpage of the SOFIA school website. Then, so these moment zero maps are basically done for the entire velocity range of -30 to 35 kilometers per second. Now, if we want to see different structures in a region, what we need to do is we need to check these moment zero maps at different velocity intervals. So for example, we were able to disentangle the shell structure of RCW49 by making the moment zero map only in the velocity window of -12 to 0 kilometer per second. We were able to disentangle the northern and southern clouds by making these maps for 2 to 8 kilometer per second, and the ridge can be made by integrating over 16 to 22 kilometer per second. So one can really see how the gas is moving and how we can disentangle these different structures, which are actually along the same line of sight in this region of RCW49. Now, for the rest of my talk, I will mainly focus on the shell, and I will in detail explore the kinematics of this shell in RCW49. So the goals that we want to achieve by the end of this presentation is to know if this shell is expanding, what is its radius, what is its speed, what is actually driving this shell, because there needs to be a powerful source which is responsible for this for the shell to expand or to move. And we also want to know the morphology of the shell. So coming to step 4, which would be to make velocity channel maps. These are just emission maps in different velocity intervals. So for example, for the shell, I'm going from -12 to 2 kilometer per second to see how this shell is progressing. And the interval between and the gap between the two channel maps is of 2 kilometer per second. So you can see that as I'm moving from left to right, this shell is basically expanding and it has broken open in the west. This is a small script that you can use to make these velocity channel maps. And I can also show you right now how this can be done. And it's quite simple. So I have to open the class section. Before that, I'm just selecting my file that I want to use. So I open the class session. We have to start with let name, which I have been doing for viewing all the LMV or mean files. And then I do let type LMV. Now, instead of go view, we do go bit here. And these are all the channel maps. However, I know which one is the first one and the last one that I'm interested in. So I will just name it here. So I will go let first 35 and let last 42. go bit again. And yeah, so now we have the exactly same channel maps as I showed you in the presentation. The only difference is that here these channel maps have contours on top of it, while the ones in the presentation I showed didn't have contours. And if you want to make these changes, you can go through the tutorials that are on the resources page of the school. Yeah. So coming back to the presentation here. Now, there's another way of looking at these velocity channel maps, that is to plot them on the same figure. So here we have these maps for C+, 12CO and 13CO. And you can see that in C+, we really see this shell. It is like an American football shaped shell. And in blue, we have the emission, which is within the velocity range of -12 to -8 kilometer per second. And in red, we have the emission from -8 to -4 kilometer per second. You also see that there's a shift, there's a small shift between these two colors, and that is basically representative of an expansion taking place. So till now, we have seen that there is an expansion, but it is in spatial distribution. The question is, do we see this expansion also in the spectra? So for that, this is the image of a moment zero map of C plus in the entire velocity range of -30 to 35 kilometer per second. And we want to look at the spectra along this white dashed line. So as we move from east to west, we are actually moving in this plot from top to bottom. Now you have to look at the lower velocity component, which is the blue shifted velocity component, because that is the one which is corresponding to the shell of RCW49. And if you look closely, the peak of this blue shifted velocity component is basically, it has a sequential shift from 0 to -12 to -4 kilometer per second. And this sequential shift in the peak of blue shifted velocity component is a signature of an expansion. So we have established that we see an expansion in that there is an expansion in the shell of RCW49. The next question is to characterize it, like what is its expansion speed, what is its radius, what is the what is the central position? So what is powering this shell? So for that, we will make position velocity diagrams. Now, what are these and why are they important? So for example, if this is a uniformly spherical shell which is expanding uniformly, then its projection on a PV space will be an ellipse. A very good description of this is presented by Butterfield and collaborators in their 2012 paper and also in their thesis. So if you're interested, please take a look please take a look and go through these documents. So for example, if I make a cut along this shell, in this shell, along this blue line, which is the diameter, it is the longest chord, we see that so on the PV space, we will see an elliptical formation, which will be like this. And it will be the largest ellipse. So we will have the largest radius and the velocities, which will be the expansion velocity. And if we make a slice along this red dashed line, which is a smaller chord, we will get a smaller ellipse where the radius and velocities are a function of cos of theta, where theta is this angle shown here. Now, how do we make these PV diagrams? I have shared this script here, and I can again quickly show it to you how one can easily do it with Gildas. So I have to open a class session. Now the command that we need to use is run slice, because in principle we are cutting slices along our shell. So you have to put in the input file, you have to select the output file, And you have to also define the starting and the ending positions of x and y coordinates, which are just the coordinates in RA and DEC here that I'm using. And if you do okay, so the task is completed and we can check what all we have. So this was the file where this is the output file with the slice. So I do let name. Instead of go view, I do go nice here. And this is the PV diagram we get for the longest cut in the shell. And you can see that one can fit an ellipse, but of course it's not perfect, but then nothing is perfect in our field, and this is what we get. So I'm going back to the presentation, and yeah, and you can see that this was exactly the same PV diagram that I just showed you, which you can make along this white dashed line. So what are these PV diagrams telling us? So we fit the best, so we try to have the best fit ellipse in here, and we then calculate these different parameters for the shell. We find that the systemic velocity is 1 kilometer per second. The expansion speed is about 13 kilometer per second. The center is very close to Westland 2 cluster. So although we need much more detailed quantitative analysis to say if the shell is driving this, if the cluster is driving the shell or not, but we can still have an idea that probably it's the Westland 2 cluster which is driving this shell just by the kinematics of this region. The radius of this shell is about 6 parsecs. Now, coming to the end of the exploration of kinematics, we have to look at the morphology. So, and in order to find the morphology, we have to compare data in different wavelengths. With SOFIA, we have the C plus data, which is tracing the PDR shell, which is here, and it's peaking away from the Westland 2 cluster. But if you compare it with the X-ray data peaks very close to the Westland 2 cluster, which makes sense because X-ray data is tracing very hot plasma, and the gas which is closest to the Westland 2 cluster should be hottest, while the gas which is further away from the ionizing source will be cooler, which is the PDR shell, which is dominated by far UV photons. Then there was also a dust morphology that was derived by Churchwell and collaborators in 2004, where they found that there's a transition boundary beyond which the dust emission got very weak. And this transition boundary is where, after which we see our C plus emission peaking. So and they also showed that the shell has broken open in the west. Putting all this information together, we can actually come up with the morphology of the region. So this is Westland 2 cluster, and very close to it, we have the hot plasma, which is then surrounded by the ionized gas, which is traced by radio data. And in the end, we have the C plus expanding shell, which is a PDR shell that is moving at the speed of 13 kilometer per second. But this shell broke open and a lot of plasma is leaking out. We also did a lot of energetic analysis, but the kinematics itself tells you a lot about the morphology of this region. So these were the goals with which we began, and we were able to accomplish all of them by studying the kinematics. We know that the shell is expanding, we know the radius, we know its speed, we have an idea that the driving force is Westland 2 cluster, and the morphology is that the shell is expanding, but it broke open in the west, and it is releasing the plasma outside. Before I end my talk, I want to quickly advertise the Photo Dissociation Region Toolbox, which was very well introduced by Archana Som in her talk today. So as she also said that this toolbox it helps you in deriving the physical conditions in the ISM. For that, you need to have your observed lines. For example, if all you need is 2 or more lines, and there's a big list of observed lines that there's a big list of lines that are included in the PDR toolbox. And if you have 2 or more of them, then you are set and you know the densities and G naught values. For example, this is an overlay plot of different ratios, observed ratios. And if you put them all together, you can derive the density and G naught value. If you have mapping observations, then you can have G naught maps or density maps basically. You can also use these your data points of mapping observations on phase space diagrams like I did for RCW 49 for different regions. We just overlay the data points on a grid of different ratios on a phase space of n and G naught. N is the density. You can also fit H2 data, and one can derive G naught and N again. Like Archana already mentioned, it is very easy to install. And yes, I forgot to mention, but this PDR toolbox is basically developed by Mark Pound and Mark Wolfire at the University of Maryland in the astronomy department. And you can install it quite easily. And there are notebook tutorials with full documentation that already have some input sample data in them. So you don't even need your own data. If you just want to play with it and get a feel of this toolbox, you can just directly install it, go to the Jupyter notebooks and start plotting and seeing how to derive physical conditions in the ISM. So with that, I would like to say thank you and end my talk. And please feel free to ask me questions and send your scripts if you want. I can check them for you or send my detailed scripts as well. Thank you.